Okay, so my name is Amber. I'm a researcher in Cambridge. I am not a geneticist. I am a neuroscientist, so I don't know very much about genes. I'm mostly going to be talking about biomarkers, and biomarkers, I'll explain everything about what that actually means, and also how we use biomarkers in a big new European study called AIMSA trials. So we've already heard about autism and some of the challenges for autism research, and one of the big things is that autism is very common nowadays. About 5.5 million people in Europe have autism, and that influences the way that they communicate and experience the world. And about 70% of those people also have psychiatric or other medical co-occurring conditions which can affect their well-being, such as anxiety, depression, or epilepsy. And there's also been a lot of research around how autistic individuals have a reduction in quality of life and lifespan. And it's been difficult to create or develop therapies because autism is so diverse. That it's different between people, but it's also different across your life at different ages. So AIMSA trials, which stands for Autism Innovative Medicine Studies 2 trials, it's a long name. This is a research program, and we will explore the biology of autism to be able to tailor therapies and treatments and develop new medicines. So this will put Europe really at that forefront of autism research. And Louise's group is part of this big consortium, together with about 47 other big companies and universities and public bodies. So, like I said, AIMSA Trials is an EU-based research program, but we have also a lot of other international collaborations with, for example, the US, Israel, and South Africa. It's a public-private partnership, which means that we have public bodies such as universities and NGOs collaborating with companies. And it's funded by the EU Horizon 2020 program and the Innovative Medicines Initiative. The program includes, you can see it's 113 million euros. That is not all cash. Some of that is in-kind contributions, and what that means is that people will give their expertise or give us access to data or might be able to give us some materials for research. So the cash itself will only go to the universities and the public bodies, and the companies will actually give us only sort of their in-kind contributions. So this consortium started last summer, and it will continue for 5 years. So hopefully we will be able to do quite a lot in the next 5 years. So AIMSA Trials, the research program itself, includes a range of studies carried out by different groups, and we'll explore how autism develops from birth to adulthood, how this varies between different people as well. And we will look for those biological markers. So these can indicate whether a person has or may develop certain characteristics. We'll also test medicines to help with social difficulties, repetitive behaviors, and sensory processing. Obviously, we'll do that for those who want or may choose to use medications. And we'll also be preparing Europe to pioneer large clinical trials for future medicines by building a network to connect researchers and clinicians and the autism community. So we're hoping to improve and accelerate that process of developing new medicines. And of course, we want to have a lasting effect on change, and a meaningful impact. And we're going to do that by exploring policies in the EU around autism and suggesting changes for autism services in Europe. And we're also going to be doing that by developing a lot of educational tools to improve understanding of autism. So our expected impact is we're hoping that we will contribute towards personalized approaches that are tailored to biological profiles or cognitive profiles to increase lifespan and improve quality of life. So, what are these biological markers? We're also calling them biomarkers just for short. So these can be genes, they can be patterns of brain activity, or a score on a cognitive task, so how we think, or a questionnaire. And we've heard today that various specific genetic differences have been linked to autism. But there are also many common combinations of variants that are related to autism. And as we've heard, our genes influence how our brain develops. So one example of that is how efficient our cell-to-cell communication is. If there, for example, is a problem with our cell-to-cell communication, this can lead to problems with how our brain or network communicates. Some of that we can measure with brain scans, and other things we will have to look more at molecular biology. So ultimately, those differences in brain communication can be measured perhaps in behavior, such as difficulties with social interaction and communication. So what we're trying to do is to identify how these biomarkers might predict how a person develops across age and how they may respond to certain therapies or treatments, and really identify who might actually benefit most from certain therapies. So these differences in autism are estimated based on deviations from typical development at a certain age. So the ovals that you see here represent subgroups of autistic people who may have a particular characteristic at a particular age. So in the left panel, the difference is only seen, for example, in a subgroup of autistic individuals in middle childhood, whereas in the image on the right, there might be two subgroups with opposing effects. So for example, in early childhood, you might see too much connectivity in the brain, whereas in later sort of middle adulthood, later adulthood, you might see underconnectivity. So we need to figure out sort of how do we know which people fit in which subgroup? So as today we've mostly been discussing biomarkers from a genomics perspective, we've been discussing how differences in one or multiple genes may help identify different subgroups. But most autistic people don't have just differences in specific genes. So for those people, we really want to understand whether we can identify differences based on other information. And I'm just going to walk you through one of our studies that we're doing at the moment. So one of the studies that we're running is called the LEAP study, the Longitudinal European Autism Project. And this is a study where we've had participants come in between the ages of 6 and 35 years old. And we're not just testing them at one particular time point, but we're looking at, we're following these individuals over the course of a couple of years. So we're trying to understand their pattern of development. And we are working with multiple groups across Europe to get much larger sample sizes than we could get at just one particular site. And we have about 800 people participating in the study in total. So examples of clinical information that we collect are, for example, clinical assessment, both with the person themselves and with the parents. Cognitive tests try to capture differences in how people think. So examples of cognitive information are tests of general ability, like IQ tests, but also understanding how people process information by, for example, tracking their eye movements when they're looking at a video. Examples of biological information could be aspects of brain structure and function that we can measure with MRI scans, or looking at, for example, certain proteins or other factors that we can measure in blood or in saliva. So, identifying which aspects of people's profile might be distinct can help us identify those subgroups. And then these different subgroups could be mapped onto potentially shared or distinct profiles. So for example, in this particular figure, clinical profile A might be characterized by sensory difficulties, whereas clinical profile B might be characterized by a particular pattern of socio-communicative difficulties. So once we understand which people fit in which subgroup, we might be able to suggest which therapies or treatments, if people want them, might be better suited for those people in those specific subgroups. So what are these biomarkers used for? There are several different types of biomarkers that we distinguish. And these are classified based on what they are used for. So diagnostic biomarkers help to diagnose autism. For example, we might want to identify if there are differences between symptoms between men and boys and women and girls, and find out that if we understand those differences, this could help reduce misdiagnosis in girls. A likelihood biomarker helps to predict who may develop autism before they display autistic behaviors. So an example could be a family member with autism. Stratification biomarkers try to group people with similar characteristics together. So for example, people who have a similar pattern of brain activity during, for example, a particular cognitive task. And then there are also other biomarkers that look at more long-term outcomes. So prognostic biomarkers predict a person's future development. For example, how their symptoms may progress through childhood and the likelihood of developing co-occurring additions such as anxiety or depression. And predictive biomarkers can help clinicians to decide what therapy, if wanted, may be most desired and helpful to different individuals. So within AIMSA trials, we'll be identifying biomarkers for autism, and we'd like to confirm that these biomarkers identified also work in larger groups of people, such as people from different countries. As already was said, research is very restricted to certain particular countries, so we're hoping to really expand that to other countries as well. And we'll also integrate any new findings from molecular research studies, just studies looking at cell models of autism. Then we'll compile all of that data into one big database, and then we'll try to understand if there are certain patterns that we might be able to find. So we're including data from that, how we think, the clinical presentation, brain function, structure, sort of everything together. And that's quite new. That hasn't really been done before. So the only official biomarker that's currently acknowledged is intellectual disability or learning difficulties. And obviously this is very helpful for certain reasons, such as knowing when to make appropriate adjustments for therapies. So clinicians could, for example, adjust their language and use visual aids in case where maybe you want to provide talking therapies to reduce anxiety. That might make it more accessible for the autistic person. And although this biomarker is able to distinguish between two groups, that's not really enough to really use personalized approaches. So we'd like to identify at least one more biomarker, and we will submit this for official approval to the European Medicines Agency. The European Medicines Agency is a decentralized agency of the European Union, and it's responsible for scientific evaluation, supervision, and safety monitoring of medicines in the EU. Having the biomarker submitted and approved by the EMA makes this then an official biomarker, and this means that it can be used by everyone in healthcare and research. So identifying a biomarker and going through this process could be helpful for the development of future biomarkers as well, and the use of these in sort of general practice. So I'll just give you an example of what these biomarkers could do. And it's important to know that these biomarkers don't necessarily have to be used for medicines. They can be used for all types of therapies, behavioral therapies, talking therapies, anything. So for example, a diagnostic biomarker might help us to identify whether a child may have a higher likelihood for developing autism. A likelihood biomarker might then predict if this child may develop language difficulties. As with stratification biomarkers, we can identify what type of subgroup this child might fit into. Then with prognostic biomarkers, we might be able to identify and predict how their language development may progress. Based on this information, we can then identify and suggest therapies that might be most helpful for this child. So hopefully I have explained to you and you now understand what a biomarker is and how different biomarkers might be helpful. If we want to move towards a future of personalized support, biomarkers could be very helpful. But, of course, not everyone will know what biomarkers are. So, as part of our research and our project, our research program, we will use our European Autism Research Network, which is a network linking clinicians, researchers, the autism community, the general public. And we will use this network to train and promote the use of biomarkers for researchers, clinicians, and the autism community. And we'll hopefully also have a science exhibition around this as well. So we're really trying to make it accessible. And we'll also be working with a group of autism representatives from across the EU. And they will be able to give us input on biomarkers research, and hopefully we will be working together towards more collaborative research. Of course, to work towards more sustainable change, we'll be presenting a 10-point autism health plan to the EU to suggest policy changes that may facilitate those personal approaches as well. So, thank you for listening. And I know we're not taking any questions, but if you have any questions, just write them down. Thank you.